A meter installation like this measures the amount or volume of liquid flowing through it. In gallons or barrels, the meter register tells us how much liquid petroleum or product has passed through the meter. Since the exchange of petroleum and product is based on meter readings, the readings must be accurate. However, no meter can be absolutely accurate. Wear, friction, and limitations in its design can all cause inaccuracies. So at specified times, once a month for example, meters have to be proved, tested for accuracy. Once a meter is proved, its registered quantity is adjusted to a reading of the required accuracy. It can be done mathematically, as you'll see in this program. Or it can be done mechanically. Either way, and any proving job, always follow the recommendations in the API Manual of Petroleum Measurement Standards, Chapter 4. Several types of provers are available, but in this program we'll discuss pipe provers. Pipe provers can be permanently mounted, and some can be portable. A new type is the small volume pipe prover. Some pipe provers are unidirectional. Some are bidirectional straight type, and some are bidirectional U-type. This is a common type of pipe prover, so we'll use it to name some parts and tell how it works. Overall, a bidirectional U-type pipe prover consists of several valves and connected pipes. The U portion, or loop, at one end gives it its name, U-type. The prover is connected to the main line, the line carrying the liquid being metered. Here, the prover is installed downstream from the meter, but it could just as likely be installed upstream from the meter. Before a proving run is made, the outlet and inlet valves to the prover are closed, and the mainline block valve is open. So liquid flows through the meter and on down the main line. To divert liquid flow into the prover, the inlet and outlet valves are opened and the mainline valve closed. Even with the inlet and outlet valves open and liquid flowing through the prover, flow through the meter continues. Thus, the meter operates throughout all proving runs. A four-way diverter valve on the prover controls the direction of flow through the prover. Here, the valve's positioned so that flow goes to the right side of the prover in a counterclockwise direction. And here, the valve's positioned so that flow goes to the left and clockwise. Remember, this prover is bidirectional. That means it's designed so that one proving run is not complete until flow goes through it first in one direction and then the other. A four-way diverter valve allows you to change the direction of flow in the prover. But you should know that in some older provers, 4 separate valves were used to accomplish the same thing. Notice the 2 detector switches. They're connected to an electronic meter proving counter with electric cable. The counter, in turn, is connected to a pulse generator on the meter. Between the detector switches lies an accurately calibrated part of the prover. It's called the prover's base volume. The base volume is certified to deliver a very specific round-trip volume of liquid, like 10.02806 barrels, for example. This is a displacer sphere, a ball, that's normally inside the prover. Before a proving run begins, the displacer is in one of the receiving traps. Here, it's in the right trap, but it could just as well be in the left trap. It doesn't matter. So in this case, flow is directed to the right side of the prover, and liquid forces the displacer toward the base volume portion. As the displacer moves past the detector switch, a signal is sent to the electronic counter. The counter then begins to register pulses put out by the pulse generator on the meter. The pulse generator is attached to the meter. It puts out a large number of pulses for every gallon or barrel that the meter registers. For instance, this pulse generator puts out 16,800 pulses for every 1 barrel it measures. A high number of pulses per barrel or gallon breaks down the meter's volume measurement into very small increments. This allows a much finer and thus more accurate measure of the meter's indicated volume. As the displacer travels through the base volume portion of the prover, the electronic counter continues to operate and measure the meter's indicated volume. When the displacer reaches the other detector switch, it trips it, and the counter stops registering pulses. The displacer goes on into the left receiver trap. But this is only half of the proving run. To complete it, the 4-way valve is turned to send the displacer back through. And once again, the displacer actuates the detector switch, and the counter starts counting meter pulses, adding to the number already counted in the first half of the run. Finally, the displacer travels past the other detector switch, and the counter stops registering pulses. This completes one proving run in a bidirectional pipe prover. Now we can read and record the number of pulses counted during the run. Here it's 85,357. Remember, this number, when converted to gallons or barrels, tells us the volume the meter registered. Ultimately, it's compared with the certified volume in the prover's base volume portion. However, because accuracy is so important, several proving runs are made. Here, for example, are the pulse counts for 10 different runs. Notice that 5 of the 10 total pulse counts are very close to being the same. The actual number of proving runs required depends on the policies of the involved companies. But the main idea is to make enough runs to ensure repeatability. That is, enough runs have to be made so that a certain number of pulse counts falls within acceptable tolerance. For example, here are the pulse counts for the 10 runs again. In this case, requirements called for 5 consecutive runs out of a maximum of 10 to be the same or very close to the same. In this case, the last 5 are acceptable. Once the required number of proving runs are made, several calculations have to be done before the job's finished. We'll go into that later, but first, let's go back and review what we've learned so far. Several types of pipe provers are available. This is a permanently mounted one. And this one's portable. Here's a unidirectional pipe prover. And here's a bidirectional U-type prover. A typical bidirectional U-type prover consists of several valves and lines. Liquid flows through the prover when the inlet and outlet block valves are opened, and the mainline block valve is closed. Usually, a 4-way diverter valve controls the direction of flow through a bidirectional prover. Between the 2 detector switches lies the base volume of the prover. The prover volume is calibrated and certified to deliver a very specific volume of liquid. The detector switches are connected to an electronic meter proving counter via electric cable. The counter is electrically connected to a pulse generator on the meter. When the displacer contacts one of the detector switches, the one at right here, the electronic counter begins counting pulses from the meter pulse generator. Then, when the displacer contacts the other detector switch, the counter stops counting pulses. Now, this is 1/2 of one proving run. To complete the run, the displacer is sent back the other way. When it contacts the detector switch, the counter starts counting pulses again and adds them to the number counted in the first half of the run. When the displacer contacts the other detector switch, the counter stops registering pulses. This is one proving run through a bidirectional prover. The number of pulses are read and recorded from the counter. These pulses are converted to gallons or barrels and tell us the volume the meter registered during the run. This volume will be compared with the calibrated base volume of the prover. However, Several proving runs, 10 are shown here, are made to obtain the needed accuracy. Also, further corrections are required before meter and prover volumes can be correctly compared. We'll go into this later, but first, if you have workbooks, stop the tape and work exercise 1. Then return to the program. Now let's go through a typical meter proving. Let's watch a proving technician prove a meter at this meter station. He'll use a portable bidirectional pipe prover. First thing he does is attach a grounding cable from the prover to the meter skid. Grounding the prover prevents the buildup of any static electricity that could spark and cause a fire. Next, he removes the caps from the prover connections on the meter facility. He attaches the hoses from the prover to the connections on the meter station. He should be careful not to spill any oil on the ground. Once the hoses are attached and secured, he opens the prover inlet and outlet valves and closes the main line block valve. Oil now flows through the prover. Oil is allowed to flow through the system while the technician continues his preparations. This allows the temperature and pressure in the prover to stabilize and any air or vapor in it to be displaced. Also, he checks for leaks in the system. No leaks are allowed because all the oil must flow through the meter and prover. Any leakage won't get measured, and that's not permissible. External leaks may only require that he tighten the fittings. On the other hand, internal leaks are something else. The technician is opening an internal leak detector, a small valve at the base of the main valve. Opened, it allows liquid to flow out if the main valve is not fully sealed closed. If the main valve leaks, he'll stop the proving run and get the valve repaired. Otherwise, some liquid would flow directly into the main line and not into the prover. The liquid that bypassed the prover would not be accounted for, and the proving would be invalid. After making sure there are no leaks, next step is to attach the pulse generator to the meter and connect one end of a lead to the pulse generator and connect the other end of the lead from the pulse generator to the electronic pulse counter. Then he connects the leads from the detector switches to the pulse counter. Next, he tests the counter to make sure it's working right. Normally this means following a test sequence provided by the manufacturer. Since a proving run is not valid if there's air or vapor in the system, the technician has to bleed off any air or vapor that may be trapped in the prover. Usually, bleed valves are provided on the prover. He bleeds vapors before and after each proving run. Remember, air or vapor takes up space in the prover that should be occupied by liquid. Since the prover's base volume is calibrated for vapor-free liquid, vapor pockets can cause erroneous results. Once the technician's sure that the flow rate, temperature, and pressure are stabilized, that there are no leaks, and that no air or vapor is trapped in the system. He's ready to start the first proving run. To do this, on this prover, he flips a switch to actuate the four-way valve. This launches the displacer. With the displacer launched, he now turns his attention to the flow rate, temperature, pressure, and gravity of the liquid, oil in this case, being metered. The volume of oil measured is affected by all these items. Also, he'll eventually compare the volume measured by the meter with the known calibrated base volume of the prover. But to do this accurately, both the volumes through the meter and through the prover must be corrected to standard temperature and pressure. These standards are 60 degrees Fahrenheit and 0 psi. In other words, regardless of what the volumes are at their actual temperature and pressure, they're converted to what they'd be if they were at 60 degrees Fahrenheit and 0 psi. Next step is for the technician to determine the flow rate of the liquid through the system. Now, this is important because flow rate affects the amount of slippage through the meter. In other words, liquid is forced through clearances in the meter. Higher flow rates cause more slippage. Lower flow rates cause less slippage. The amount of slippage affects the volume of liquid measured by the meter. So, the technician records the flow rate on his proving report. In this case, it's 900 barrels per hour. Let's look closer at this form he writes his data on. Some type of proving report is used by the technician to record all the pertinent data in the proving operation. For example, this one has spaces for the location, date, ambient temperature, and report number, as well as prover and meter data, which includes such information as prover base volume, meter pulses per barrel, manufacturer, and so on. Run data includes the temperature of the prover and meter, pressure on the prover and meter, total pulses for each run, and at bottom, averages for each item. Spaces are also provided for liquid data, field calculations to arrive at corrected prover and meter volumes, and the calculations needed to determine meter factor. Finally, it has spaces for any remarks and for signatures of the companies represented in the proving operation. Returning to the proving operation, the technician reads the temperature of the oil at the prover's inlet and outlet. This because liquid volume changes with changes in temperature. If the two readings are different, he averages them. Since liquid volume also changes with changes in pressure, he reads the pressure at the meter. If both inlet and outlet pressures are available, once again he'll average the two. If the meter is not temperature compensated, he reads the line temperature at the meter during the proving run. However, some meters are temperature compensated, which means they have a device that automatically corrects the metered volume to 60 degrees Fahrenheit. If so, the technician doesn't have to obtain the temperature at the meter. In any case, the technician records all his temperature and pressure data on the proving report. Changes in the gravity of a liquid usually mean changes in the liquid's thickness, and the meter has less slippage with thicker liquids and more slippage with thinner liquids. This affects the volume of liquid measured by the meter. So the technician obtains a sample of the oil to measure its API gravity. He must withdraw it either upstream or downstream from the meter and prover, since the proving run's in progress. During a proving run, he should not take the sample between the meter and prover. Remember, every bit of liquid that goes through the meter must go through the prover. After properly obtaining a sample, the technician measures its gravity and temperature. Then, using an API conversion table, he corrects the gravity to the standard temperature of 60 degrees Fahrenheit. Gravity readings must be corrected to standard temperature. Finally, he records the API gravity at 60 degrees Fahrenheit on the proving report. In this example, it's 39.0 degrees. By now, it's time for the technician to turn the four-way valve and send the displacer back the other way. This completes one proving run. Now, before we continue, let's do another review. To make a proving run, the technician must ensure there are no leaks in the system, either externally or internally. He tests the pulse generator and electronic counter to ensure they're working properly. Before and after each run, the technician bleeds off air or vapor trapped in the system. Otherwise, invalid proving runs may result. Since flow rate, temperature, pressure, and gravity of the liquid all affect the volumes measured in the proving run, the technician records the rate of flow of liquid through the system. Next, he reads and records the liquid's temperature and the pressure. He obtains a sample and measures and records its API gravity at 60 degrees Fahrenheit. If you have workbooks, stop the tape and work exercise 2. Once the technician completes a proving run, he reads the total number of pulses for the run and records it on the proving form next to the temperature and pressure readings for the prover and meter. Total pulses for this example run is 85,402. The technician makes several additional proving runs by switching the four-way valve actuator in order to launch the sphere. He makes enough runs to ensure repeatability. That is, he makes runs until he gets the required number of pulse count totals that fall within required tolerance. For instance, in this case he made 10 runs. Requirements call for 5 consecutive runs to be in agreement. So, he crosses out the 5 that are off and averages the totals for the acceptable runs. In this case, the average prover temperature is 72 degrees Fahrenheit. Since the meter is temperature compensated, he simply writes TC. The average pressure at the prover is 88 psi. The average pressure at the meter is 92 psi. And the average pulse count is 85,359. Now he divides the pulse average by the pulses per barrel to figure registered or gross meter volume, the volume the meter registered during the proving run. In this case, it's 85,359 divided by 16,800, which gives 5.0809 barrels. Now this registered meter volume must be corrected to standard conditions, and we'll see how this is done in a moment. He also enters the prover's base volume, which in this example is 5.0991 barrels. The prover volume must also be corrected to standard conditions before it can be compared with the meter volume. To do this, the technician's concerned with several things. First, since the steel the prover is made of expands and contracts with changes in temperature and internal pressure, he must determine corrections for this effect. The corrections are abbreviated as CTS and CPS. CTS stands for Correction for Temperature of Steel, and CPS stands for Correction for Internal Pressure on Steel. The liquid volume also changes with temperature and pressure, so he needs 2 more corrections, CTL and CPL, correction for temperature of liquid and correction for pressure on liquid. To find values for CTS, CPS, CTL, and CPL, the technician uses the appropriate API tables. For example, this table is in Chapter 12, Section 2 of the API Manual of Petroleum Measurement Standards. It gives CTS values for mild steel, which is what a lot of provers are made from. As an example, if the observed temperature of the prover was 78 degrees Fahrenheit, this falls between 73.5 and 78.8 degrees. So the CTS value is 1.0003. This figure then goes in the CTS space provided on the form. In a similar way, the values for CPS, CTL, and CPL are found and also entered on the form. These figures are all multiplied together to find the corrected prover volume, 5.0731 barrels in this case. The technician finds corrected meter volume in a similar way. He uses the value for CPL and multiplies it by gross meter volume. Note that no CTL value is needed because our example meter is temperature compensated. Also note that no CPS or CTS corrections are needed for the meter. At any rate, the corrected meter volume works out to be 5.0834 barrels. With this information, the technician can now calculate the meter factor. He multiplies the meter's registered volume by the meter factor to correct registered volume to actual volume. To find the meter factor, the technician simply divides corrected prover volume by corrected meter volume. In this case, it's 5.0731 divided by 5.0834. This gives a meter factor of 0.9980. This figure is recorded in the meter factor space on the report. It can now be used to correct the meter's registered volume. Simply multiply the registered volume by the meter factor. For example, if the meter registers 10,000 barrels, multiplying it by 0.9980 corrects the reading to 9,980 barrels. Before any proving run is accepted as valid, the technician should ask himself a few questions. Did he check for external leaks? Any leakage between the meter and prover will mean that the volume is not the same through them. And how about internal leaks? Once again, any leakage inside means the meter and prover volumes won't be the same. Did the pulse generator and electronic counter check out? How about bleeding off any air or vapor trapped in the prover? A meter registers air or vapor as liquid, so none can be trapped in the system. Was the rate of flow the same for each run? Flow rate affects the amount of liquid slippage through the meter. Did temperatures and pressures remain stable throughout the proving operation? Liquid volume changes with temperature and pressure. Were all proving runs the same API gravity? Changes in gravity mean changes in the liquid's thickness, which affects the rate of slippage through the meter. Were all the necessary temperature and pressure corrections made? And are they correct? In fact, are all the calculations correct? Check the math and make sure the figures are all copied down correctly. If the answers to all the questions are yes, then you've probably got a valid proving. If you have workbooks, work exercise 3.